Hello, everybody. Good afternoon. Of course, again, it's a great pleasure for me to be here at Devoxx. And my name is Edson Yanaga. I'm currently a Director of Developer Experience at Red Hat. My Twitter handle is @Yanaga. And just in case you're wondering, or if you didn't know that yet, yes, I'm a Brazilian Japanese. I know that there are other Brazilians at the conference, but I think I can tell that I'm the only Brazilian Japanese here. So it's such a unique combination. Okay. And today I'm going to talk about microservice data patterns, CQRS, and event sourcing. I introduced a bit this subject on my talk on Monday, but today we're going to explore even further this topic. So I'll start over with some explanation again. I also happen to be a Java champion and a Microsoft MVP, which kind of shows that the world has changed a lot, and we're living in a very different world. And last year, I had the opportunity to give a talk at Devoxx with the subject, Migrating to Microservice Databases. This was the result of the last 2 years of research. I've been talking with different teams and developers worldwide, trying to figure out how they solved the problem of splitting and later integrating the data in microservices architecture. So in this book, I covered the subject of how can we split and integrate the data using relational databases. But after that, I received a lot of different requests. I talked to a lot of more people about the subject again, and I realized that some pieces were missing because it's not all about relational databases. We have different use cases, we have different scenarios, different requirements lead us to use different technologies to solve different problems. That's why I decided to go even further on my research. And again, in the past year at least, I was able to collect even more useful tips for if you're considering using microservices architectures. And just as I said last year, of course, this is an oversimplification, saying that code is easy and the state is hard. Code can be hard too, but no matter how hard your code is, I think that in most enterprise information systems, the really hard part is your data. Because the data is something, I'm pretty sure that most of the code that you write today, it won't be running 10 years from now, but I'm pretty sure that most of us enterprise developers, we are dealing with legacy data, and this data might have been written into a relational database like 30 years ago, and we still have to manipulate that. It might be we're dealing with legacy schemas, and we probably have to deal with that in the upcoming years too. So data is a special point in any architecture. There is no system that doesn't manipulate data. You always have behavior and you always have data. But I've seen that many people, when discussing distributed systems and microservice architectures in general, they only talk about the general architecture of your code, and sometimes they forget about the data. That's why I decided to pick this topic, to go even further and try to explain to you what is happening in the data world and how people are solving the data problems in this kind of architecture. But before I dig into the CQRS and event sourcing of today, I have to introduce a bit of context because particularly I've been reading some books and articles on the internet, and I think some people have like some, I wouldn't say wrong, but not very clear definitions of what is CQRS, what is event sourcing, why are we using this kind of things today. So I think it would be important for me to introduce a bit of context. So because these patterns, I think I can say patterns, they were created more than 10 years ago, and we need to understand why they were created at that time. So I want to first ask, how was data management managed 10 years ago? If you can remember, which were the tools, which were the context that we had 10 years ago when we were developing specifically Java software, you know? If you take a time machine, you'll go back 10 years, what were you doing 10 years ago in your daily development activities? You would say that 10 years ago, you were pretty terrified about entity beans, because many of us had to deal with entity beans for persisting object states into relational databases. Then we magically had something that promised to solve all of the problems that we have with entity beans. We had Hibernate, and just to give you some numbers, in 2005, we had Hibernate 3.0, and it took like many years to have like another version, Hibernate 4. Java 6 were released in 2006. so approximately 10 years ago, 11 years ago. And Java E5 and JPA 1.0 were released in May 11th, 2006. So that's the world that we had 10 years ago. And you can bet that 2006 we had Java E5 and JPA 1.0, but it took like many years for us to be able to use this technology in production, mainly because the release cycle of the Java application servers is not like Java E was released in 2006. I bet that most of us were able to first use like JPA 1.0 in production in 2008, 2009, or even 2010. So, and maybe some of us are still using like Java E5 into production. So the release cycle for us to be able to use new technologies sometimes takes longer than we wanted to. So given this context, we had Hibernate, we had entity beans, we wanted to use POJOs in our domain model, and we still, at that time, we're still using XML to map our POJOs to our relational database. So with the Java E5, we started to think about, well, maybe we don't need to keep using XML for this kind of configuration. Maybe we can introduce some kind of metadata into our codes. So we started to think about annotations. And some people thought that it would be a good idea to have annotations everywhere. Then we had annotation hell, just like today. But at that point in time, we thought we were living XML hell. So we thought that we could get rid of everything XML and get everything into annotations. So basically, that's the context that I would like to give back 10 years ago. So instead of using entity beans, we were creating POJOs with what I call an dynamic domain model, right? We had these POJOs. Most of them were just content holders. We're just like plain POJOs with just attributes and getter setters with no behavior, mainly because of the legacy that we have the entity beans. We couldn't add behavior anyway. So the first step, well, now we want to use POJOs with Hibernate and everything else. We just try to mirror the concept that we had in the past. We're doing the same thing as before, but now we're using POJOs and maybe using some annotations. That's the context of 10 years ago. Then 10 years ago, approximately, we created another kind of architecture. Or I don't know if it was really created, but the term was coined by their event sourcing, which is a very nice architecture for some requirements. Event sourcing basically means that the state of your data is not stored anymore in a single row in a database with lots of columns where you can read and write that. The state of your data is now represented by a stream of events, usually in an append-only file system. So you're not recording anymore that like the money that you have in your bank account is 10 euros. No, you're just recording like I start with 0 and I just keep recording the debit and credit transactions until I can reach the current state of my object or my entity, my abstraction. So you might think that event sourcing, if you look at the theory and everything else, it's a very nice architecture for you for writing. You have very fast writes, but reading is not that fast because every time you want to know how much money you have in your bank account, you have to start from 0 again and keep calculating all the data back and forth. Okay? So this is the concept of event sourcing. So 10 years ago, we were starting to think about POJOs. And then we realized, well, event sourcing is a nice thing. But there was a huge gap in mindset between the technologies and tools that we're used to and this new architecture called event sourcing. And event sourcing is not fine just because we can have like a free auditing log and a free state machine and very fast writes. But I think one of the key points of event sourcing that we can benefit from today is that if you decide to use event sourcing in your architecture, events enables you to think in the events that happen in the system instead of having to think about the data structure of your systems. And think about, it's one of the dangers of like conditional thinking. We are always trying to reproduce the way that the procedures that we had in the past. So if you talk to domain experts or system analysts or architects that are like older than I expect the average of us, they used to think about SQL databases and everything else. So every discussions about the domain model always start with that. Well, now we have to model a bank account. Now we have to model a customer. And the next step is always, well, customer. What does this customer have? The customer has an ID, it has, I don't know, maybe a date of birth, maybe it has the date that where the row was created. It might have a phone number, it might have a social security number, it might have like a lot of different addresses. But if you have a lot of addresses, then I think you need to add a foreign key, then we're going to create an association. That's the typical discussion, especially if you talk to older people, because they're used to think about the structure of the information system before thinking about the behavior of the system. So that's a typical use case. And many of us, if not most of us, are also used to think about the structure instead of the behavior. So, but when you're thinking and modeling your system as an event sourcing architecture, you have to think first about the events, which means that you have to think about the things that happen in your system, and just later, you start thinking about the structure of the information that is flowing between your endpoints in the system. I think this is an important switch, because today when we're talking about distributed systems, distributed architectures such as microservice architectures, we have to think first about the things that happen in our system. We have to think about the dynamic behavior and consequently the events. And later, we think about the structure of that. I think we're switching the things that we think first. So that's an important switch in event sourcing. So now imagine, now we have this kind of information, but 10 years ago, POJOs, event sourcing, it was such a huge gap. And to try to fill this gap a bit, Greg Young, which is the person that coined the term CQRS, he used the term CQS, which means a different thing. And CQS was created by Bertrand Meyer, the guy that created the info language. And in principle, it meant command query separation. Basically meant that in your system, you must have interfaces or abstractions, and these abstractions must be split between writing operations and reading operations. So writing operations that modify the state, and reading operations should only return the current state, we should never modify the state. So that's the principle that was applied. Or in other words, I like this quote from Bertrand Meyer too, asking a question should not change the answer, which means that if you ask the same question 5 times in your system, you should always receive the same answer. Query operations should never change the state of your system. Okay? And improving on that, Greg Young needed a term for this new kind of architecture or pattern that he was creating at the time. So he decided to call that CQRS, Command Query Responsibility Segregation, which is a very fancy name for, I think now we consider a simple architecture. And I think we had some kind of confusion in the past too, because most people thought that CQS and CQRS meant the same thing. We can see that CQRS improves on top of CQS, but they mean different things. At least that's the knowledge that we have today. So if I wanted to give you a brief explanation of what is a CQRS architecture or a CQRS pattern, so in traditional enterprise information systems, the way that you want to store and read your data, just as I showed a bit on Monday, we had, if I want to have a customer abstraction, I create a customer class, and this customer class has all the dependencies, address, phone number, and everything else. And I use this customer class for writing. So if I'm using JPA, I get my entity manager, I ask my entity manager to store and to save, to merge my customer instance. And when I want to read that, I just create a JPA query, and I retrieve all of the information from the customer into memory. I populate the POJO back again, and maybe I extract this information to show to the user. This is the typical CRUD architecture. But you might think that it doesn't perform very well, because if my customer class, my abstraction, has a lot of different dependencies, like if I have like my customer class has a lot of fields, and maybe on the screen, of course, all the fields won't fit on the screen. If my customer had like 20 different fields, and he had like, I don't know, 10 join tables, and I just wanted to show on the screen the customer ID, the name, and the phone number, I would have to retrieve all of the information from the database, populate all the POJOs, just to show 3 different fields on the screen. So it doesn't perform very well, and the more complex your entity is, you get even worse performance. So when we create CQRS, we created what we called at that time DTOs, data transfer objects, which are different from the entity being ones. And we call that data transfer objects because they're just placeholders for information. They don't have behavior. They are truly anemic, but they're just supposed to mimic the exactly same view that you would have on your screen, right? So if you have a web system, you just query the fields that you want to show to the user. So now you created a CQRS architecture because you're still writing, populating a customer instance and writing that to your database. But for reading operations, you're instantiating another class, which is customer DTO, and you're showing that to your user on your screen. That's the simplest possible CQRS architecture, okay? And of course, you will have different, if you're using a repository interface, for example, it's a good practice to have one set of interfaces in your repository for writing and another set of interfaces for reading, because you might even use different technologies for reading and writing. As I said, the simplest possible architecture is just create separate classes, domain classes, but you might be even reading and writing your information from different data stores implemented in different technologies. So that's why it's important, this segregation. And if you think about CQRS, this very simple CQRS architecture, of course, then you start thinking that you can improve on top of that. And today, for distributed systems, the most common architecture that we have for data distribution and integration is CQRS with separate data stores. You have different models for reading and writing, and you're reading and writing from separate data stores. When I say separate data stores, it means that you might have different sets of tables and columns in the same database, or you might be writing your information in an event store. You might even be writing your write operations in something like MongoDB, but reading from a SQL database. Or you might be writing to like an in-memory data grid and reading information using like some stream processing analytics cluster. You might be using Apache Spark to process some real-time analytics. So today we're starting to use different technologies for the write and read operations. So that's an important thing that we have to have in mind, because again, the most common architecture for CQRS these days in distributed systems is separate write and read data stores. And CQRS and event sourcing, it's very common for us to be applying these architectures together today. I'll explore even further the discussion. But I'd like to say that when Greg Young created this term CQRS 10 years ago, he intended CQRS to be an intermediate step between traditional like CRUD information systems, just like using the same model for everything, to an event sources architecture. So he thought that, well, maybe if we introduce CQRS as a step between, we first separate the read and the data models, it will be easier for people to grasp event sourcing and then migrate, which I believe that holds to be true. And I talked a bit about this on Monday too. But I think that CQRS proved to be such an useful pattern that we're using that in many different use cases these days, not just for event sourcing. I think they're a perfect fitting CQRS and event sourcing, mainly for performance reasons, but I'm going to explore with you from now on why you should be using CQRS in other use cases and which are the technologies that you should be using depending on the requirements that you have in your data. So, why CQRS? Classical reason for using CQRS is performance. If you have, you're not allowed to just retrieve all of the customer information in the POJO for your query, or you might even want to perform some critical aggregation, and you don't want to perform this aggregation in memory. It's much more efficient for you to be performing this aggregation on the database using your aggregation capabilities of your SQL database. So performance used to be the first reason for using CQRS architectures 10 years ago. But now that we have distributed systems, microservice architecture, we're using CQRS architectures for things like distribution, availability, integration, and analytics. So distribution is that now if in a distributed architecture for microservices, if each one of the microservices must own its own database, which means that the owner of the microservice data is the microservice itself. So you have different pieces of information that is scattered around your architecture. But If you have just the pieces of the information, it's very hard for you to do something useful, because data usually needs to be correlated with other pieces for you to process anything in an enterprise system. So you need to integrate and correlate the data to generate any useful output. And also, so distribution and integration. But you also, if you have a distributed system, now you need to take care of the availability of your system. Because now if the customer information is only on that microservice, and that microservice goes down, I'm not allowed to break my entire system just because I don't have the customer information. But if you think about behavior, many people think about circuit breakers and everything else. Circuit breakers are a nice solution for the behavior part. But if you need the data that is on the customer service and that thing is down, how are you going to finish any kind of computation that needs that data if you don't have it? So you're also distributing your data and integrating your data to improve the availability of your system. Maybe you need a local cache or a mirror copy of the information that is from the customer microservice here on your monolith or your other microservice, because you want to improve the general availability of your system. So availability is an important part, and analytics is becoming very, well, the main theme of Devoxx this year is artificial intelligence, and most of us are thinking about using some process of machine learning, and to have machine learning we need lots of data, and one of the easiest way for you to generate the data that is flowing through your system is through events, right? So events that are being distributed in your system are a very important source for your analytics process, because we want to generate even more knowledge from the information that we have stored today, or that we have in our system, but since we're not storing the events that are happening anywhere, we can take the benefits of all the information that we could have in the system. Okay, so the typical use case here for CQRS is that I have a canonical source of information, which can be your enterprise system, or can be your new microservice. Yeah? Again, you don't need to be creating multiple microservices architectures to take the benefit of CQRS, because you can use your old legacy monolithic application to generate events and create a CQRS that is stored for analytics, for example. And some people use this kind of thing for data warehousing in the past too. So data warehousing, you're basically creating a CQRS model to perform some queries outside your production database. So it's the same principle here. So you have your canonical source of information. Doesn't matter if it's microservice or monolith. Then you need to create your distributed CQRS read data stores. Each one has one specific purpose. If I had a customer microservice, maybe I'm creating here a CQRS read data store because I want to improve the performance of this part of the system with a local copy of the data, or I want to improve availability. Or in the other case, maybe I'm creating another CQRS read data store, just as I said before, just for analytics, right? Or another reason for me to be doing that, I might have some sensitive information in my canonical source of information that I don't want to be hacked. So if I have like some medical records or social security number information that shouldn't be exposed to the public, and I don't want to be like threatened by an old struts version that might not have been patched in production, then I don't want to have like my production of database being exposed to the public with that part of the system. Maybe I want to tie, well, this public API will only consume the records that are supposed to be public, and the sensitive information will be stored in the separate database. So you can create a CQRS read data store with just the information that you want to make available to the public and serve that in a different server. Right? That's another valid reason for you to be creating a CQRS read data store. But since you're basically now creating read data stores, which you can think about cached copies, because they're just supposed to be used for reading, and the writing always happens on the canonical source of information. And I have to open a parenthesis here. When I say canonical source of information, I'm saying that this data store is the only one that is allowed to have writes. It's different from canonical model. I think I made some confusion on Monday. Canonical model is that old legacy thing that people thought that, well, my entire enterprise needs to agree on a common model. You see, everybody has different requirements, but we must have a common model. This is a canonical model. Here I'm just saying it's a canonical source information, meaning that the true point, if you want to see if anything is really right, you go to the canonical source information, because all of the other ones, they might be wrong or outdated, right? That's the other endpoints. But if you have these other endpoints, you have your canonical source information, you need to update this read data stores somehow, and that's where events take part of an architecture, right? The easiest way for you to be updating your read data store is through events, and that's where you have your event source in architecture. Like the flow of information for you to be updating your reads, CQRS read data stores is through events, and you have many different techniques for generating these events. Okay? And since I've explained this concept already, now let's go that different choices of technology depending on the requirements that you have on your data and your application. Some considerations that you need to have in mind when trying to consider an architecture or technology to be solving your problem includes latency. When I mean latency is that I have the source of information, I have my read data store. Latency can have different meanings depending on the context. Latency can be how much time does my data change gets to be propagated from the writing data store to my read data store. Okay? How much latency do I have with the current network connections that I have from here? Right? Am I writing my read data store? Is that on a local network, or I have a geographically distributed data store? Some of considerations. Other kind of latency, we can consider that business latency. How long can my business application wait to receive an update from the canonical source information? Does my so if a record gets updated right now, if I wait like 5 seconds for that information to be updated, will I have a strange behavior in my system? Or if I wait like 30 minutes, it won't matter because users can work with the information that they have from 30 minutes ago. That's another consideration that you need when choosing technology. Size. How big is the data set that you must replicate? And again, how big are the changes that you need to transfer from one endpoint to the other? It also influences the technology that you will choose to solve your problem. Staleness. How frequently your data gets updated on the canonical source of information? Does it get updated like 5 times per hour? Or does it get updated like 10 times per second? Or 100 times per second, right? These kind of requirements change the technology that you will choose to implement this architecture too. Ownership. Who owns the canonical source information? Is that your own enterprise system that is owning the information? Is that a database server that is owned by another team inside your own company? Or is that an external service? You're just consuming your data from an external provider. So that's other consideration that you must have too. Security, which is basically which subset of the data is sensitive, as the example that I gave before. How much of the data do you want to have the liability of exposing to the public? So that's another consideration. And type. I said type, I'm not pretty sure if type is the right name for these requirements. But say, depending on the type of information that you want to share, you must think about type. Is it important for me to be always correct, to be always current with the latest information? Do I need to store the whole history of the events in my CQRS data store? Or my data is simply ephemeral, right? Is something like traditional enterprise system information, or is something like trading information, where it doesn't matter if I lose like a lot of records, I only need the latest one. Or if I have an IoT system collecting sensors, doesn't matter for me the old values. No, you only need the latest information. Okay, so these are some considerations that you need when choosing your technology. Now we'll go into the technology part. Which kind of technology is suitable for each one of these problems? So the first technology that I want to cover is in-memory data grids. In-memory data grids. Well, of course, you're storing everything that you have in memory, and you might have the benefits that you already know. For example, most people use in-memory data grids for caching. And that's a very simplistic, how do I say, problem to solve. You can also use in-memory data grids like for session externalization. These days, since we're talking about 12-factor applications, and you need to externalize the sessions to an external storage, you use in-memory data grids for that. You have many popular data grids in the market. Most of them are open source. You can use like Redis, you can use Memcache. But what I want to tell you today is about InfiniSpan, because I believe that it has some very nice capabilities, not only caching and external session storage, but we can have other capabilities that help us a lot. So in-memory data grids, for example, they can have sharding. If you have an InfiniSpan cluster and your business is geographically distributed, and well, if you think about, maybe the data from the Brazilian customers is better to be stored in Brazil, because that's where you're going to use that. So you might have a distributed cluster, and you just shard information depending on the geography that you are. So if you store just European customers here in Europe, Brazilian, Latin America customers in Brazil, and so on. Also, you might be using sharding for regulation purposes. Maybe your country has a specific requirement that the data from your users must be stored inside the country. Sharding, that's another interesting application. And keep that in mind. Your data must be sharded, because I'll use that in another example. If you really need fast transactions, if you have a massive volumes of transactions in certain moments of the year or the day, for example, if you have an online ticketing application and you sell tickets to music shows, and you know that everybody's waiting for that new show that somebody famous might be releasing. And yeah, I don't have a nice example right now. But then everybody, when you release the sales, everybody wants to buy the same tickets at the same moments. And usually traditional relational databases, they don't cope with the demands. So you need something very fast that can give you this kind of support. Usually you use an in-memory data grid for that. If you need real-time analytics, you need to know if something is happening right now, and you're not allowed to wait for a Spark cluster or a Hadoop cluster to give you the analytics that you want to show. You need really some fast data. We call it fast data. If you need the results now from the analytics, maybe you need something like an in-memory data grid. And one of the things that I want to discuss too is that some in-memory data grids, it's the case of InfiniSpan, they have some features which you call continuous queries. So if you're able to store your source of information in an in-memory data grid, the traditional way for you to know if your data changed is you're storing your data here, you create a query, you apply the query to your data sets. Then you compare what I had before and what I have now. Maybe you have a control row saying that, oh, this one was changed after this timestamp or something else. Then you know which of the records changed after the specific timestamp, or which were modified with a certain flag. This is traditional way of thinking, but you might bet this is also called polling. You have to keep polling with the query to know if anything changed at all. Traditional way to know if the data set has changed. Another way for you to be achieving that is what we call in the in-memory data grid terminology, continuous queries. Instead of indexing the data and applying queries to that, you do the opposite. You index the query and apply the data to the query. So that's a very interesting scenario that you can use for that. And instead of using a pull-based approach where you need to keep polling the data sets for changes, you can use a push-based architecture. So you just simply receive the changes in a reactive way or something. So I have a very short and quick, simple example that I can show to you here. If I just cast some code, I have an embedded InfiniSpan cluster in the application. I just created a class called developer, and I have different languages, and each developer has a name. You have different languages that you can choose from: Java, JavaScript, Python. Java, of course, we love Java. JavaScript if you want to be a masochist, and .NET if you're in the wrong conference. But if I say here, I just created an application. I just instantiated the data grid. I create some 100 developers already. Then every 100 milliseconds, I'm creating another, I wait 200 milliseconds between creating a new developer and putting that on my data grid. And what I create here is what I call a continuous query. I just create a query, it gets indexed on the InfiniSpan cluster, and I say, I want to filter all of the Java developers that have an A in the name. So every time a new Java developer, which has a name and the name gets added to the cluster, I want to get notified of that and perform some operation. So what do? I create a listener, a continuous query listener, and it's a callback. Every time it happens, I get notified, and in this example, I'm just showing you a simple sysout. So if I execute this, you can see that in the beginning, I already had a lot of Java developers populated. And now every time that I randomly generate a new developer which has an A in the name, which is a Java developer, I get this information printed here because that's my callback running. And it seems, well, it takes some time because we don't create new Java developers so fast. And sometimes we get a new Java developer with an A. So that's what I call continuous query. I'm pretty sure that you can imagine some nice applications, because if you are able to index your data set in memory data grids, in fact, if you're able to index your queries, you can easily use this listener to start to push the event notifications through the other CQRS read data stores. So if you need to reply very quickly to changes in your data set, probably any memory data grid is the easiest way for you to generate your events. So that's some of the considerations. And also, other considerations that you might have. InfiniSpan, for example, has this feature too. Is distributed processing. So again, traditional way for you to process your data. You have your data there. You have a relational database. Your applications connect to the database using a network connection. You execute a query. You extract. You filter. You extract all the data from the database server. You get all of this data through a network connection. You load that into memory. You process that. You modify something, and maybe then you write an update back to the database. So traditional way for you to process information in enterprise system is you move the data to where your code is. You process that, and then you move the data back. It works because usually you have a low latency network and a high throughput network between your application and your database. But if you have geographically distributed data sets, just like the ones that I mentioned, that you can have like sharding in your information, or if your data set is very big and you have a huge cluster and you don't want to replicate all of the information, so you have like different machines in your cluster, they have different parts of the data sets, you can use what we call distributed processing, which is the concept, which is not new, but finally in 2017 we were able to use that in production. You create your code, and the code gets serialized to your cluster, which is where your data is, and your query, your code is executed in the cluster, which is very close to the data. It's processed there, and you just stream the results. So distributed process means you're not moving the data, because usually the data is the big part. Your code usually is small. You move the code, it gets processed on the grid, and you get back the results. And since you can use sharding in any memory data grid, the memory data grid is supposed to be fast already, but if you have a huge data set that is sharded, it gets even faster, because your query is running in parallel in multiple different nodes in your system. You just can get back all of distributed queries and aggregate, like, I don't know, if it was 10 instances, you get back 10 subsets of your query, and you can, if you're computing an average, it's very easy for you to be doing that just with 10 different results. You just consolidate the results back again in your application. Okay, so, and distributed processing. Continuous queries is a push-based model. Distributed processing is a pull-based, because you're moving the code and you have to wait for it to come back. So you need to initiate the action. Another way for you to be creating your CQRS read data model is through data virtualization. Yeah, and you might thinking, I know it's a complaint that some people say to me when I talk about it. If you create virtual databases as a kind of a sort of view for your distributed read data store, it's not really data distribution because virtual databases are still reading from the right data store. So it doesn't allow, for example, real distribution or failover, but certain data virtualizations like TIDs can be tied, for example, with an embeddable or a local InfiniSpan or the technology in-memory data grid application. So you can apply cache to your virtual databases. So when you apply virtual databases, data virtualization, with a local cache, you are able to achieve better performance because you're not reading from the right data store. And you also have a local cache for data availability, because even if the production database goes down or your network connection to the production database goes down, you still have the local cache and your application, your remote application, or remote microservice can keep running on that. And when would you use data virtualization for that? Because it sounds like something legacy. You need a data virtualization platform because that's the easiest way for you to split and distribute and integrate your data. If you need advanced reporting capabilities in your remote endpoints. So if you have like complex queries, just like the one we're using in enterprise systems, you probably want a CQ database on your remote endpoint. And the easiest way for you to create that is using like something like a data virtualization platform. And of course, all of the things that I'm showing you today, they are all open source. You can start using them for free tomorrow. Should we use message brokers? Very much likely you will be using a message broker for distributing your events. In a data virtualization, you don't need message brokers. In the book that I showed you in the beginning, you can use other technologies that don't need message brokers, like database views and materialized views, to be achieving this architecture too. But I'm not to discuss that today. You can use message brokers, for example. You can use ActiveMQ, or everybody these days is talking about Kafka for event sourcing systems. Really depends on your requirements. Again, if you have a trading system, or if you have like an IoT architecture where we have like multiple devices just streaming to you the values of the current values of the sensors. If you're measuring temperature, for example, it's sending to you a new information every 10 seconds. It doesn't matter if you lose like 3 of the last 10 reads, because you can even that way you can have the latest value, and you can calculate the average over the day. So it's not really important if you lose any of the messages. The same of the trading system. If your stock is rising or declining, you only really matter for the about the current value. So you can use something like JMS topics for that. You don't care if you lose some of the message. You really want to know if you're receiving the latest message, so because you need just the latest information. But if you need something, like most of the enterprise systems, if you need to receive the events in the exactly same order that they were produced, if you're not allowed to lose any of the messages because it would lead to inconsistent state on the other endpoint, then you might be using something like Kafka, which is a distributed streaming platform. And the nice thing about Kafka is that each one of the consumers of your bus can consume the message in their own pace, because it's a pool-based broker. So you never overwhelm your endpoint. And since it's persistent, it's durable. It's not forever, for example, but if you have a big enough persistent storage on your bus, you can read the message from the last week or last 2 days. Really depends on your requirements. If your endpoints allow it to stay 1 week offline, then you need more than 1 week of persistence. Then that's some of the things that you need to tune when using a Kafka bus, right? And you wouldn't need a Kafka bus if your events, the data that is being propagated on the events are CRDT, conflict-free, replicated data types. But again, CRDT is a complex discussion in distributed systems. Very rare data types are CRDT, so I'll skip the discussion too. And next. Okay, you might also be thinking about choosing a reactive platform for implementing your your CQRS architecture. And let me tell you why it's useful for you to use a reactive platform. For example, if you have like you are hiring some service from Amazon or from a third-party provider, from Google or from Microsoft. And usually these third-party providers, when they provide a public API for you, they charge you for a certain number of requests. So every 1,000 requests, you're going to pay a certain amount, which is completely fine if you only have one endpoint in your system. But now that we're scaling and distributing multiple instances of your system, you're not allowed to have a pool-based architecture, and you have like, well, I have like 15 different microservices in my architecture. All of them need that information, and each one of my microservices, they have 10 instances, so I have like 150 endpoints in my system querying that public API. You can tell that your Amazon bill will be very high in the end of the month. You just allow everybody to be connecting, directly polling your remote endpoint. So what can you do? You can create like another microservice, and I suggest you to do it in a reactive way for you to be able to scale very well. And you don't, in this kind of application, you don't need relational database persistence or anything else, so you're pretty cool. We have a very small microservice for that. What you can do is you can create a reactive endpoint here. It can hold some internal state, or if the internal state is too big, you can use an in-memory data grid to store this ephemeral state. So basically what you do, this endpoint will query the remote API. So it will hold a cached copy of information, and this endpoint, you can configure that depending on the staleness requirements that you have. It will execute the polling of the remote endpoint to check if the information that you're receiving now is different from the information that you have cached here, the ephemeral storage. If anything changed, you can use Vertex, for example, to propagate the changes through a Kafka bus or a JMS topic for the other clients to be consuming. Or you can even use your Vertex application to create a replica of the public API. So your internal clients will be querying your internal endpoint and not the public one. It will save you the costs of having like 1,000 requests per second coming to the public endpoint. So that's another very nice application. So you can have, even though public APIs, public HTTP APIs are traditionally pool-based, if you add Vertex to a reactive platform that can stream to your Kafka bus, for example, you can create an almost push-based depending on the staleness requirements that you have on your public API. Okay? And the last one, change data capture. It's very interesting that I'm talking about CDC right now, because Gunnar, which is the lead architect of the Devoxx project, is giving a talk showing Devoxx at the exact same time in another room. But just to explain to you what is change data capture, it's an event sourcing architecture too. But how do you generate the events of the changes? If you don't want to mess with your current legacy architecture, but you have physical access to your database server, you can plug a CDC2, and it starts reading directly from the database transaction log. And for each one of the insert, update, delete, and alter something that happens inside your table, the CDC2 can read the transaction log and create a message that can be propagated through the message bus. And in particular, Devoxx can read from MySQL, PostgreSQL, MongoDB, and they have work in progress for Oracle and SQL Server, I think, but you would have to check with Gunnar to be very precise. So basically, it reads that, it generates a JSON payload that can be broadcasted through your Kafka bus, and any of the clients in your system can use this push-based architecture to read these JSON events and replicate the data that you need. You can see most event sourcing architectures that you're coding your type of events, you probably want to use domain-level events, which means that, well, oh, I have a bank account. I have account overdrafted, or I have account closed, and not just simply somebody added money, somebody withdraw money. So you have domain-level events if you're coding the events. But for certain types of system, which is the example that I want to give you now. You might use low-level events because insert, update, delete, and alter table are very low-level events, are much closer to the database operations that you have. And these kind of events, they don't give you the semantic value of a domain event, but and you might say, well, this is a big disadvantage. I would say no. It's a very low level, so it's very easy for you to just filter the fields that you want and that you don't want to create your CQRS read data store. And that's I think the greatest benefits of low-level events is that you don't have the power of domain-level events, but you also don't have the coupling that domain-level events give to you. Many people think that, well, since we're using messaging, we have a low coupling between the endpoints, but people forget that if you're using domain-level events, every time you create a new event, or you change the type or the semantics of the event, you have to change all of the endpoints of your system to be prepared to handle this change. But if you have low-level events, such as insert, update, delete, they're such a low-level events, you can't it will never change. It will always insert, update, and delete events, so it's much easier for you to couple with changes in your architecture. And I'm already over time. That's what I wanted to discuss with you briefly about that. I'll be publishing some articles of these different strategies, and I'm trying to also to create a very nice demo integrating all of these different technologies, and I hope you'll be able to check that later on my blog or on my Twitter. And again, thank you very much.